All right, and we're back. We have a few more talks left. We're almost to the finish line. Our next speaker, I think everyone here is familiar with Sniff, the mastermind behind Pentester Lab. He's also a huge hacker educator himself. I was one of the lucky people that got to go to AppSec, California and see the longer version of this talk in LA area. And I'm excited to see what he has in store for us this time around. You guys ready? Should we get right into it? All right.
Hey everyone, so if you are watching this video, it's probably because my Australian internet didn't work, so hopefully it's going to be as fun. I'm going to try to join still in the chat and stay around. So today I'm going to talk about JWT and two specific fields inside the JWT header named JKU and X5u, and how they can both bring a lot of love, or at least good bug bounty money. So about me, so I'm a security engineer. I do pen test, code review, security consultant. I'm also the person who runs Pentester Lab. You probably have heard of it, hopefully. If you haven't, you should probably check it out. It's a pretty good way to learn AppSec and to get better at bug bounty. So make sure you go to pentesterlab.com. And that's my Twitter handle, Pentester Lab. And you can also find me at Sniff if you want more personal things. So a lot of people are using JWT for OAuth 2, for session, to manage trust between systems, to do password reset. And a lot of people as well who care about being stateless between multi-data center or multiple application. Let's say you have a lot of microservices. You want them to talk to each other and pass the data through the user and back to another microservice. JWT is a pretty good solution to that. But JWT are very complex and they can bring a lot of cool bugs. A bit of crypto 101. Let's get started. You have two main things in crypto: encryption that gives you confidentiality, amongst other things, and signature that gives you integrity. And sometimes encryptions give you integrity as well, but let's keep focused on these two things. When you do signing, you have a secret and you're using, for example, HMAC, or you can have a private and public key and using asymmetric crypto with RSA and elliptic curve or other things like that. When you have a secret, you sign with the secret and you verify with the same secret. So both systems need to have access to the secret. If you're using RSA or asymmetric, you have a private key to sign and a public key to verify. And the public key is public, so even if you have access to the public key, you can't sign messages. So that's the main thing to remember about basic signing for JWTs. So the JWT format, so it's JSON Web Token. So first, in JSON Web Token, obviously you have JSON, so the JavaScript object notation, and it's just a human readable format to store and transmit objects. So here we can see that we have a person, we have first name, last name, age, hobbies, address. This is just structured using JSON. If now we look at JSON Web Token, so we have three parts: the header, the payload, and the signature. They are separated with a dot. The first and the second part, so the header and the payload, are just base64 encoded JSON. So base64 of a curly bracket and double quote. So that's why you can see EYJ when you look at JWT tokens. So if you see something that matches EYJ something dot EYJ something dot something else, you are dealing with a JWT token. Header and payload are base64 encoded JSON, as I said, but it's not really base64. It's URL safe base64 encoding without padding. And the signature is also base64 encoded. So what's the difference between base64 and base64 URL encoding without padding? First, you base64 encode, then you remove all the equal sign at the end. That's your padding. Then you replace plus by dash, because plus doesn't work in HTTP really well because it's used as an uncoded space. And you replace slash with underscore because slash doesn't work really well with HTTP because it's used as a separator for paths. And then you return the string. The header contains an algorithm attribute. Here it's saying like, oh, this token is signed using HMAC 256. And this is to tell people receiving the token how it was signed. A lot of different algorithms are supported. Non, HS256, HS384, the RSA family, elliptic curve, PS, which is just RSA with a different padding. So now The payload in the middle can contain literally anything, username, roles, whatever you want to put in it. It also has like registered keywords, claims to say like, oh, for expiry, when this token will expire, or AIT for issued at, to say when that token was issued. And then let's look at how you create a token. So first you create a JSON header and base64 encode it. Then you create the JSON payload and you base64 encode it. Then you concatenate with a dot the header and the payload. You sign the result and you base64 encode the signature, and then you append it to the end with a dot between the payload and the signature. When you decode a token, so when you're verifying it, you split the token in 3 parts based on the dot. You base64 decode each part. You pass the JSON for the header and the payload, and from that header, you can retrieve the algorithm. So that's a lot of work to do before you can even check the signature. Then you verify the signature based on the algorithm, and finally, you verify the claims to make sure, for example, that the token hasn't expired. You have a lot of attacks against JWT, so non-algorithm, that is pretty well known nowadays, so you can just use none to say like, don't sign this token. Trivial secret, so if you use a simple secret, people can brute force it offline. Algorithm confusion, that is a bit more complex. It just, when the application is using a private and public key, you can use the public key to sign the token and say, instead of being an RSA token, it's now an HMAC token. The JWT also allows people to use like a key ID to retrieve the key, and you can try to inject as part of the retrieval of the key to, for example, bypass authentication or gain code execution. Another funny one is a bug in Cisco Not Jose, CV 2018-0114, where the library was trusting a key that was embedded in the header. Now that we know a bit more about JWT, let's jump in JKU and X5u. So if you read some of the JWS, so JSON Web Signed Token RFC, you probably learned about JKU and X5u. If you don't read RFC, you should. And when I looked at that probably 4 or 5 years ago, no one was using that. So I was a bit disappointed. And then I found out that people start using it more and more. As part of the header, you can have 2 parameters, one named JKU and one named X5u. So JKU is JWK URL and X5u is X5C URL. The former links to a JWK, so a JSON web key at a certain URL, and the second one linked to an X5C, so an X509 certificate at a certain URL. So this is what a JWK looks like. So it's just a way to encode a key that can be used to verify or sign a token. Here it's a public key, so it's only used to verify a token. So here the key can be used with RSA. You have the public component, N and E. You have a key ID, and you use to say like, this is how the key can be used. And this is what a JWT key looks like. Same for X5C, but instead of having N and E, you got X5C, which is just a base64 encoded certificate. And then you got the usage, so you can use it for signature, and the algorithm that is recommended, RSA 256. And the X5u is just a link to that. So let's see how it works. So you have a user that is sending a JWT with a token in it. The application passes the JWT to extract the JKU header. Then it fetches the JWK based on the JKU header, and it passes the JW key, and then it's verifying the JWT signature using the JWK, and it's returning a response. So that's the classic case. No one is doing anything malicious yet. If we look at what an attacker can do, so it's going to send an HTTP request with a malicious JWT. The application is going to pass the JWT to extract the JKU. Then it's going to fetch the malicious JW key based on the JKU, so from the malicious server. Then the application will verify the JWT signature using the malicious JWK. And since the attacker controls both the JWK and the token, they can say, I signed this token with this key, and make the key available to the application. And that can allow you, for example, to bypass authentication on a server. Unfortunately, or fortunately, if you're part of the blue team, most libraries don't do that. It would be too easy to bypass authentication if you were to do that. So they block access to malicious JWK. They have a list of allowed URL that you can use. But turns out filtering URLs is incredibly hard. For example, some library will use a regular expression and say it needs to match trusted.example.com. The problem is that they forget to escape the dot, and you can use trusted.example.com, and you bypass the check on the URL to make sure it's part of a list of allowed domain or URL. Other solution is to use starts with. And the point is that you can use starts with and say like it starts with trusted, but you can go to http://trusted@pentesterlab.com or trusted.pentesterlab.com, or you can say trusted/jwks, but you can .. your way to another file, or you can .. your way to an open redirect, or you can .. your way to a header injection. So starts with is not a really good way to validate URLs. Ideally, you would use something else, but you can use it as long as you canonicalize the URL before making sure it starts with something you trust. So let's see how it works with an open redirect. So again, we're sending a JWT. The application passes the JWT to extract the JKU, and it's fetching the JWK from the trusted server. But we have an open redirect on the trusted server. So what we're going to do is leverage that open redirect to get the application to fetch the token from our server. Redirect the application to the malicious server. The application, instead of fetching the key from the trusted server, now is fetching it from our malicious server, thanks to the open redirect. One limitation you may run into is that the HTTP client used by the application to fetch the key does not follow redirects. So it's not always exploitable, even if it starts with and you have an open redirect. Maybe the HTTP client inside the application will block that attack. Then it passes our malicious key, and it's verifying the JWK signature using the malicious JWK, and we're in. Another thing that is pretty cool is that we can leverage header injection to do the same thing. Again, we're going to send a JWT. It's going to be passed, and the application is going to extract the JKU header. The application is going to fetch the JWK based on the JKU header. And this time, we have a header injection. So what we can do is use the header injection to reflect the JWK in the response. So we're going to create this very long URL that exploits the header injection to add a JWK in the response via the header injection. And the application is going to pass the JWK, but this time it's going to pass the JWK from our header injection. It's going to verify the signature with the JWK from our header injection, and it's going to return a response back to the user. And hopefully we should have successfully bypassed the authentication for this application by crafting a malicious JWT. So the exploitation is simple. You find a header injection, you use the header injection to return the JWK, you add the header injection as the JKU, and you assign the token with the key in your header injection, and you should be in after that. Another issue that is pretty common is the RFC call out enforcing TLS to avoid someone manipulating the response. What the issue is that few implementations don't understand that properly. What they do is, instead of enforcing that the string starts with HTTPS during the retrieval of the key, they enforce it when you create the value. Basically, when an attacker sends a malicious token, this attacker controls the URL. And that's the URL you need to make sure starts with HTTPS when you're fetching the token. Just checking that the URL starts with HTTPS when you create the token is just not enough. Conclusion, use strong keys and secret. Don't store them in your source code. Make sure you have key rotation built in, so that's basic JWT hygiene. Review the library you pick. Don't take like a library that supports JKU and X5u if you don't need it. Make sure you check the signature. Make sure your token expire. Enforce the algorithm. Test for X5u and JKU if you're doing bug bounty, because even if an application is not using them, the underlying library may, and you may be able to bypass authentication or at least get a server-side request forgery inside the infrastructure. Don't burn open redirect, because they can be used to chain vulnerabilities together and for example, bypass authentication if you're leveraging the Open Redirect to fetch a JWT. Read RFC because that's the source of truth, and hack all the things. Final conclusion, JWT are complex and kind of insecure by design. Make sure you check Pazeto, should be a bit better than that because it's less agile. JWT library introduced very interesting bugs, so that's why it's always worth looking at those. JWT is such a complex format, but it's a really interesting thing to audit. It's that fine line between crypto and application, so like crypto engineering. And that's something that is really interesting because even if you're not like a math wizard, you're going to find cool bugs. And make sure you test for those if you write code, pen test, or do bug bounty. Thanks for your time. If you have any question, you can email me, pentesterlab.com, @pentesterlab or @sniff. And that's about it for me. Thanks.